So everything becomes very clear now. If I consider some signal m of t, let's say this is my signal m of t. In the beginning, output of counter will be 0. The counter will be in reset mode. So counter will start from all 0. And output of the DAC in that case will also be 0. So initially counter will start from 0. You can see that output of DAC is 0. M of t and m cap t will be compared. M of t is greater than 1. That means output of op-amp will be plus Vsat. It will be held at the output side and given to a final output device in the form of logic 1. Now that 1 means counter has to count in upward direction. So counter will count to the next state. Counter counts to the next state, and you can see the output of DAC will also increase by 1 step size. M of t is still greater than output of the counter or output of the DAC, which is m cap t, and hence you can see that output of op-amp will also be logic 1 again. So that means it will be plus Vsat, which will be taken as logic 1. If that logic 1 is given to the counter again, the counter counts in upward direction. So counter counts by 1 again. You can see output of DAC will remain to this fixed value. Now why output of DAC will not change and it remains constant? Because output of counter will change only when there is a valid clock pulse. So in one clock period, output of counter does not change, and hence output of DAC also does not change. You can see when the next clock pulse arrives, the output of op-amp will be again plus Vsat, because you can see m of t is greater than m cap t. That means SOT will be logic 1, and hence the counter will again count in the upward direction. So by now we have taken 3 logic 1 on the output side, and for all these 3 logic 1s, the counter counted in the upward direction. You can see once again at the end of the clock period, m of t goes slightly above m cap t. That means output will be again logic 1, and hence counter will count in upward direction. But this time you can see m cap t is greater than m of t for the very first time. So when the next clock pulse arrives, the output of op-amp comparator will be 0, and for that case counter will now count in downward direction. This time we can see m of t increases then m cap t, so output will be logic 1 again. So now I hope you understand that this will continue in such a way that the ones and zeros will be produced based on the nature of m of t. So whenever m of t is increasing, you can see initially output was logic 1. When m of t is decreasing towards the end, output is logic 0. Now in between, if you observe, m of t was almost constant, not changing, not increasing, not decreasing. In such a case, m cap t will fluctuate around that particular constant value, and this will give us 1 0 1 0 etc. So finally my s of t will become digital representation of analog input m of t. Now the question is, how do we recover m of t? So on the receiver side, when we receive ones and zeros, we will use a device which will again start from reset, that means 0 point. The first input will be logic 1, that means I have to increase the output of the device by a fixed step size. So basically I'll again use a counter and DAC structure. So when the control input to the counter is logic 1, it will count in upward direction. For first 4 logic 1s, the counter will count in upward direction 4 times by fixed step size. So the DAC output will also increment 4 times. Now next input bit will be 0, that means counter output will decrease, it will count in downward direction. For 1, it will count in upward direction. For 3 zeros, counter will count in downward direction. So you can see on the receiver side, we will generate this step-like signal with the help of up and down counter and DAC. And finally, this step-like signal will be passed through a low-pass filter. If you pass it through a low-pass filter, then this step-like signal will become a smooth signal, and you can see it will resemble to my original modulating signal. So this black color signal was original modulating signal, and this blue signal is nothing but recovered modulating signal. So you can see the recovered signal looks very much similar to the original signal, and that's how the entire system of delta modulation operates. However, it looks as if delta modulation will be much more efficient compared to PCM, because for every one sample we are transmitting only one logic bit, either 1 or 0, by simply comparing it with the previous sample. There are few drawbacks associated with delta modulation. So let's discuss the drawbacks of delta modulation, and then we will also compare it with pulse code modulation.